afternoon everyone, welcome to a sunny worked exam answer video where today I'm having a look at an AQA question that combines a bit of a calculation with some tests for different ions, and those include ions from sort of the year 12 inorganic chemistry side of things, and then also one from the year 13 inorganic side of things in the aluminium 3+ ion that is present. So 6 marks, and there is quite a lot to do in this 6 marker as well, because we've got to work out the formula of this water soluble mineral shermagite. Yeah, any clues on how to pronounce that in the comments would be grand. We need to work out its empirical formula so that we can work out what the M represents and work out the value for X in terms of how many waters of crystallization there are. And then for these 3 ions, we need to describe the tests with their results, including ionic equations that would confirm the identities of those 3 ions present. So we've got the ammonium ion, we've got the aluminium one, and we've got the sulfate one. We're told that the relative formula mass is 453.2 as well, which may be helpful. Now, in terms of the composition by mass, this bit is an empirical formula calculation. So I'm just going to set up so that I have the different elements across the top to create a little table. And then have the masses of those underneath. And then the ARs underneath that. So top numbers from the periodic table, 27, sulfur's 32.1, oxygen is 16. And I've done it this way because then when I do the masses, which are equivalent to the percentages, so that's my top row here, divided by the AR, we're going to get the moles, and then from there we'll be able to work out the simplest whole number ratio, and then from there we'll be able to get the empirical formula and the value of X for the waters of crystallization. So and I'm going to give all of the answers to moles to 3 significant figures. Don't need to do the next one. 5.96 divided by 27. So then if I divide all of those by 0.221, I'm going to have 1 nitrogen and I'm going to have 1 aluminium. I'm going to have 2 sulfurs. I'm therefore going to have 20 oxygens. And I've done that just by eye, by looking at the numbers. I could have just divided them all by 0.221. And because I don't know what 6.18 divided by 0.221 is, I'm going to do that one on my calculator and get 28, which seems like a lot of hydrogen and quite a lot of oxygen as well. Now I guess for the empirical formula we could literally just write N1. We wouldn't write the 1, obviously, we're chemists, we're lazy. H28 AlS2 O20, but it also wants us to be able to work out the numbers of waters of crystallization, and it has told us that these 3 ions are present. So if I have 1 nitrogen, there is going to be 1 NH4 plus ion. There can't be any more than that. I have 1 aluminium, so there's going to be 1 Al3 plus ion, and then because I've got 2 sulfurs, there's going to be 2 SO4 2 minus ions. So that has accounted for the nitrogen, the aluminium and the sulfur. So how many hydrogens does that account for, and how many oxygens does that account for? So there's 4 H's in the NH4, so we're now down to 24 H's. And then we've used up 8 oxygens, so we're now down to 12 oxygens. Now, because water is H2O, this works out really nicely in that I need to have 12 lots of H2O, therefore X is equal to 12. However, what I haven't done, which I should have done, is check that all of this adds up to 453.2, because if it doesn't, then I might have to do some scaling. So yeah, how silly of me to forget that that was there. So nitrogen is 14, 28 ones is 28, aluminium is 27, sulfur is 32.1, and there's 2 of them, and then 20 lots of 16 is 453.2. So thankfully it's all fine, but had it have come out as being, say, 226.2, I would then need to double all of this, so therefore X wouldn't have been 12. X would have been a much bigger number. Okay, so we got past that. Then, so we've done the first part. Describe the tests with their results, including ionic equations, that would confirm the identities of the ions present. So I think the one that we're probably most familiar with is the one for the sulfate ions. So when we have sulfate ions, or we think we have sulfate ions present, you would add barium chloride, because that would provide us with barium ions. You would also need to add for something like hydrochloric acid to acidify the solution, remove any impurities that might also precipitate with the barium, and then that gives us a white precipitate of barium sulfate. So for this ionic equation, I've included the sulfate ions from the sturmagate, the barium ions from the barium chloride, and that is what we observe as our white precipitate. So add HCl, then BaCl2, observe a white precipitate of barium sulfate. And in terms of the ionic equations, the reason why it looks like this is because these are the ions responsible for forming the substance that we observe being made. And it wouldn't matter what negative ions are here, I know they're chloride ions, and it wouldn't matter what positive ions are here, either one of these, they're not going to give me, combined together, the white precipitate. So those are kind of spectator ions as such. Okay, the next one that you're probably happiest with is the ammonia one, i.e. the ammonium ions reacting to produce ammonia gas. The ionic equation for this, potentially less happy with, just because it's less familiar, but we would add sodium hydroxide solution and then we would warm it up. And again, it doesn't matter that it's sodium hydroxide solution, the key thing is that we're adding hydroxide ions. And when the ammonium ions and the hydroxide ions react together, we make ammonia gas, which is what we test for using our damp red litmus paper that turns blue. And even though that's the product that gives us the observation, we have to include plus water, because otherwise we wouldn't have a balanced equation, and all equations, even ionic ones, have to be balanced. So that's why the water needs to be there on the product side. So here we would add sodium hydroxide and warm it up, just like in a hot water bath. And then we would test for the ammonia by adding damp, and it needs to be damp so that the gas can dissolve onto the paper, by adding damp red litmus paper, which turns blue. So that would be the ammonium ions done. And then the year 13 component of this question is your Al3 plus ions. So this comes from the reactions of metal ions in aqueous solution topic. Now, I've written that, but I'm not actually going to use that in my equations, because the assumption would be that because this is water soluble, and we've got those waters of crystallization, that we would have the hexa aqua aluminium ions, so that we would actually start with Al H2O 6 with a charge of +3. And with the aluminium species, we need to know that we can add the hydroxide ions and they will act as bases and we will form a white precipitate. There are other ions though that would form white precipitates if we did that, so then we would need to talk about adding the excess of the hydroxide ions, and the aluminium white precipitate is the only one from the ones in that topic that would react with an excess and redissolve the precipitate. So we are going to need to, I suppose we could do it in two ways. We could look to just add an excess straight away, or we could break it down into two and say, well, first of all, I'm going to add just enough hydroxide ions, which would be 3, to give me the white precipitate, whereby we now have 3 water ligands and 3 hydroxide ion ligands, and that is neutral, hence it precipitates out of the solution. Plus 3 lots of water, because the OH minuses each gain a proton from a different water ligand within the complex to become water. This is a white precipitate. So we have added sodium hydroxide, and we have observed a white precipitate of Al H2O 3OH3. And then the next equation would be taking said white precipitate, adding more sodium hydroxide, and you can do this with more than one additional hydroxide ion, but I've always done it with just one extra, which means we're going to lose another proton from a water ligand, taking us down to 2 water ligands and increasing us to 4 hydroxide ion ligands, and then that is no longer a solid because it now has a charge. So this will now be aqueous, so that's going to be back dissolved in the solution. We're going to make 1 additional water molecule, and because this is now charged and in the solution, and it's aluminium, not a transition metal, that would be colourless. So I'm going to then put, upon addition of excess NaOH, the white precipitate dissolves to give a colourless solution. And that should be me done with everything now. So we've got the empirical formula, we've got the value of x, we've described the tests, the results, and written ionic equations for each thing. Perfect, job done. Now they will potentially join sort of the year 12 testing for ion knowledge with the year 13 reactions of metal ions and aqueous solution knowledge. There are quite a few questions that do this. They often want you to write ionic equations, so in these latter ones it doesn't matter that it's sodium hydroxide, it just needs to be a soluble hydroxide. Sodium's the one that I guess we would teach, but it could be potassium, and that's why these are ionic equations, because again we've not included the sodium ions in here. So those are definitely skills to learn. So this would, I guess, also class slightly as a practical question, because this comes up in RP4 and this comes up in RP11. So lots of things covered there, I think, including a calculation. Any questions, as always, guys, please just hit me up in the comments or drop me a message. And thank you so much for watching. I hope you're all doing okay, and I will be back with more videos in the next couple of days. Thank you so much for your support. Take care, everyone.